Fun. Okay. All right, so what I want to do is we should have a test on this on Monday. Monday, a week from today, we should be able to cover what we need to do for this material. And then after that, we should be able to start one of our first projects. So I think that'll be different for you. We're working in, go back in the lab a little bit, and then we'll come back and do another little unit. Then we'll do a very large lab after that. So we are going to get in the lab here just not too long from now. Well, first of all, we're talking about this thing called the measurement systems, and we're talking about this one in particular, metric system. And I thought there were things that they did that were just incredible. I don't know how they thought about this stuff actually. Number one, they decided that all the measurements that they were going to have were going to be based on this thing called the meter. And so they had to have, once they had the meter, they knew they had powers of 10. They're going to base it on powers of 10. They're going to use Latin and Greek prefixes. They weren't going to use French words or anything about a French king or anything like that. And they were going to base the meter itself on something that people wouldn't think was nationalistic. There's no nationalistic thing about the Earth. And so they said it was 1/10,000,000th of the distance from the North Pole to the equator. Now, that was a great question you had about could they actually estimate what that was? I don't know if I know the answer to that. I know that they somehow, that's a good question. Did they use pure mathematics to figure out that that thing right here, that meter stick was that? So then they, after they did the meter, we're going to talk about this, how they knew how far it was around the Earth. They knew that a long time ago. Once they made the meter, they said, now we're going to do something for volume. And they took a meter long and a meter wide and a meter high. If you made a box that big, it just was impractical. Nobody would have ever used it. So the next choice would be 1/10 of a meter. So they made the box 1/10 of a meter by 1/10 of a meter wide by 1/10 of a meter. So now, without memorizing these, and I'm going to ask you to memorize this, but there's a liter, but you know that each side is a 1/10 of a meter, a decimeter, 10 centimeters. You should be able to take all those and cube them and find other ways of representing this cube. So this is 1 liter of volume. It's also known as 1 cubic decimeter of volume. It's also known as 1,000 cubic centimeters of volume, or 1,000,000 cubic millimeters. Does that make sense? Didn't we do this last week? I want to make sure you have all these notes, right? I'm just kind of going over them. So don't sit there and act like you have to memorize them. Just know your powers of 10 and know the box is 1/10 of a meter, right? Or a decimeter. Now, the next thing they did was, and by the way, the Earth is, if that's 1/10,000,000th, there must be 40 million meters around the Earth, or also known as 40,000 kilometers, which is really close to around 25,000 miles, if you like English system there. And let's go to the next one. They also didn't stop there. They said, okay, let's do something for mass. We'll take this box, fill it with water. Later they found out that 4-degree water, 4 degrees Celsius water is about the most dense liquid water ever gets. And so they said, if you fill it with water, then we're going to call that, they could have called it a gram, but if they were dealing with little things like gold, what human likes to talk about 0.0001 grams? Nobody likes that. So they went ahead and made this a kilogram, and so that's a kilogram of mass. So if 1 liter of water, as volume, equals 1 kilogram of mass, then 1,000 milliliters of water is 1,000 grams of mass, or on purpose they did this. Yes?
Why isn't that the most dense water can get us 4 degrees Celsius?
You'll find every material, even though solids and liquids are essentially non-compressible, you can change your volume by a little bit with temperature. You can't do that. Like engineers have to watch out for this all the time. You build a skyscraper in New York, it gets really hot, it gets really cold. Even they have to worry about contracting and expanding things. Even when I build a deck, if I build a deck on the back of my house, and I put boards down, you never put the boards right next to each other, especially if it's cool. Because in the summer they'll expand and it'll warp everything. Okay, so we always have to worry about that. So they found out that every material every material, when you cool it, becomes a little less dense. So the volume, as the temperature goes down, the volume goes down, and it keeps going down for all materials. It just gets a little bit more, it's less volume, a little less volume. But water is a weird thing because water does everything other materials do until it gets to about 4 degrees Celsius. And then liquid water does this weird thing between 4 and 0. We'll talk about that in another chapter, where it actually starts expanding. And that's weird. And yet, it's one of the most important materials on this planet, and it has some very, very unique characteristics. And we'll find out about that later. But so water has to do with hydrogen bonding, has to do with how close they get together and they kind of push each other away. But liquid water is still liquid at 3 degrees, but it's actually less dense. Everything else is supposed to get more dense when you cool it. And so water kind of starts pushing itself around between 4 down to 0, and that's why even ice cubes are less dense than water. I don't know of any other materials. Frozen gasoline will not float in gasoline. Frozen gold will not float in liquid gold, but water does. So anyway, they decided to use this as liquid water's most dense temperature is about 4 degrees. That's about 39 degrees Fahrenheit. Does that answer your question at all? Or? Do I know why God made? I don't know that exactly, but
Yeah, kind of.
We have another chapter where we'll talk about how the hydrogen bonding, the polar nature of water. I don't know if we talked about that in chemistry. I think we did. Remember the polar nature is plus and minus? When it gets so close, the plus and minus nature of water starts repelling and pushing the other ones away. But we'll have that also in another chapter. So on purpose, they made 1 milliliter of water equal to 1 gram. Everything was so simple. Also, what about density? We're going to do a big density unit later here. The density of water is 1. They made it 1. That makes it everything's so simple in the metric system. So I thought that was pretty neat. So what I'd like to do is I'm going to show you a let's see. Let's see which one it is, sir. No, not that one. No. I think it was this one. I found it the other day. Did we start this the other day and you couldn't hear it? Okay, all right.
Hello, this is our science teacher, Tim Martin, and in this video, we'll talk about Eratosthenes and how he measured the circumference of the Earth 2,200 years ago. We'll also talk about how you can measure this today. Eratosthenes was an educated individual of Greek descent. At the time, like many other educated individuals, he spent some time in Alexandria, Egypt. While in Alexandria, Egypt, he read of a well a little further south in the country, located in the city of Sene. This well apparently was a very deep and straight well. He read that one time each year, presumably on the 21st of June, sunlight shone to the bottom of that well, indicating that there were no shadows at that time. He also knew that although the sun was high in the sky in Alexandria, he was able to observe shadows, as you can see from this small flagpole. With this knowledge, Eratosthenes knew he had what was necessary to measure the circumference of planet Earth. Let's back up a little bit and talk about some of the other things that Eratosthenes knew. Eratosthenes knew basic geometry. Now, geometry is far more than measuring lines, angles, triangles, and other shapes. Take apart the word geo, earth, metry, measurement. Geometry is the science of measuring the earth, and Eratosthenes helped develop many of those principles. Eratosthenes knew the earth was round. 300 years earlier, the mathematician Pythagoras helped establish the Earth was round by observing lunar eclipses. Eratosthenes knew that the sun's rays were parallel and that once a year, around the 21st of June, the sun shone to the bottom of the well in Seen. At the same time, he knew there were shadows in Alexandria, and he also knew the distance between Seen and Alexandria was approximately 5,000 stadia. That's plural for stadium, or the length of one stadium. That turns out to be approximately 925 kilometers. This measurement may be a little off because the method of measuring a great distance like this was timing how long it took traders with a camel train to make that trip. Let's take a little more look at his geometry. Eratosthenes knew that this well that was dug down in Seen likely was straight enough that it would point directly at the center of the Earth. Thus, those sun rays were pointing down towards the center of the Earth over the well in Seen, Egypt. He also knew that if you put a flagpole vertically in the ground, it too would point towards the center of the Earth. He realized that if he measured the sun angle, that angle would be equal to the central angle inside the Earth, because he realized the flagpole created a transversal that crossed parallel lines. Through basic geometry, we know that the alternate interior angles when a transversal cuts parallel lines have equal measurements. From here, if we know the distance between Seen and Alexandria, that distance compared to the circumference of the Earth is proportional to the angular measurement to 360 degrees. Let's take a look at this a different way. I like to think about a pizza. Now imagine if you have one piece of pizza left. Let's take a protractor and measure the angular size of that pizza. Now let's take a tape measure and measure the length of the crust. Knowing the angular size of the pizza and the length of the crust, could you figure out how far it is the whole way around the pizza? Of course. Let's imagine that this piece of pizza is 45 degrees and has a crust of 10 centimeters. Let's see, 45 is half of 90. 90 is 1/4 of the pizza. So that means I have 1/8 of the pizza. If I have 1/8 of the pizza and the crust is 10 centimeters,
1/8 of the
I can quickly calculate that the distance around the pizza must have been 80 centimeters. Or we can set this up mathematically. We can say the angle A, central angle, compared to 360 degrees, is proportionally equal to the arc length D, the length of the crust, compared to the circumference of the whole pizza. This is exactly what Eratosthenes did. Once he measured the sun angle at 7.2 degrees, he knew that was equal to the angle in the center of the Earth. Comparing 7.2 degrees to 360 degrees was proportionally equal to the distance between Seen and Alexandria compared to the circumference of the whole planet. Eratosthenes did this calculation 2,200 years ago and calculated the circumference of the Earth to be 250,000 stadia. Remarkably close, considering this was 2 millennia ago.
Each year, on or around the autumnal equinox, my students repeat Eratosthenes' experiment. Rather than placing a pole in the ground and trying to get it perfectly perpendicular with the surface of the Earth, we simply tie a weight onto a string. On the top of that string, we construct a flag out of tape. Then measure the length of this string from the tip of the weight to the top of the flag. As close as possible to solar noon on the equinox, that's approximately halfway between sunrise and sunset, we go out and measure the length of the shadow. Once we have these two measurements, we construct a 1/10 scale triangle using those measurements. Whether we use an electronic measuring and construction tool or make the construction with pencil and paper and measure with a protractor, we'll measure the upper angle of the triangle, which is the sun angle, equal to the angle between our location and the location where there is a 0-degree sun angle. We find the distance to the equator, since that's where the sun is shining directly overhead. For those of us in the eastern United States, we can simply look up the distance from our location to Quito, Ecuador, a sizable city in Ecuador right on the equator. With the measurement of the sun angle and the distance to a location on the equator, we then go on to calculate the circumference and then the diameter of the Earth. I'd encourage you to give this a try. And as I tell my students, when you do this, I hope your answer is better than Eratosthenes. After all, we've had 2,200 years to improve on his work. Thanks for watching.
Right. Oops. All right. Yeah. All right, so what do you think? Could you do this? Okay, let's talk about this a little bit. You asked about, well, how did they base it on the Earth itself? How did they even know that the Earth was round? Well, they knew that a long time ago. They knew that. It's kind of weird how certain people figured out that when I look at the moon on certain times, there's an eclipse. They call it a lunar eclipse. If you look at the moon and the moon's being eclipsed, they call that a lunar eclipse. Get that? So if you're looking at the moon, it's a lunar eclipse when it comes out. A solar eclipse looks like when the sun looks like something's blocking the sun. That's a solar eclipse, right? So anyway, let me pause this. Let me go through the mathematics of this a little bit, and I want you to think about this, all right? First of all, you had your hand up, and I didn't answer it at the time. Do you remember what it was, the question?
No, I got it.
First of all, he said some things. He said all the sun's rays are parallel. Do you agree with that? Like, really? Like that one going that way is parallel to that one going that way? But what did he say? When he said they're parallel, what did he actually mean? Yes?
Well, since the sun is way bigger than the Earth, two rays can come off the sun parallel to each other.
Right, so they have, they go off in every direction, don't they? But if I gave two beams of light, let's say 100 beams of light, if I gave them 100 miles and they weren't parallel, what would happen in 100 miles? They would start going off from each other, wouldn't they? If they were slightly off, they would. So we're going to give them 93 million miles. 93 million miles, and if you're not parallel to me, okay, you went that way, right? But the ones that actually strike the Earth are pretty parallel. The ones that actually make it to the Earth's surface, those are parallel. So then, whether it's a well here or even a stick in the, I call it sighting, he says seeing, right there, if it's a vertical stick or something goes straight down, it's pointing to the center of the Earth. But what if I put a stick in the ground? What if I put a stick in the ground, it's vertical this way, it's vertical this way, then it's also pointing to the center of the Earth. So I have these parallel lines right here. This is the sun rays right here. And then I'm pointing to the center, and so are you. So we have this thing called a transversal. So what is that? All you know about geometry? Two parallel lines cut by a transversal create alternate interior angles. Remember that from geometry? So here's Eratosthenes figuring it out. And he's using a little ratio here. He says, okay, what angle is this? Okay, so the angle right here at the top of the stick was 7.2 degrees for him. So what does that mean? So what? So what? It was 7.2 degrees. What does that mean? Well, was that a whole circle? What fraction of a whole circle was that? It's 7.2 360ths, isn't it? Now, I like the example he gave on this video. He said, what if I had a piece of pizza and it was a 45-degree angle? Well, a lot of you, even in your head, can figure that out, can't you? 45-degree angle, that's half of 90. That's 1/8 of the pie, isn't it? This isn't 1/8, but whatever fraction it is, he said, okay, whatever fraction it is in the world of degrees, it has to be the same ratio as in crust, like that. And I wrote down the number he had. It was 925. He said 925. I actually read a little bit about Eratosthenes, and the word stadia, or what they did is this camel train that would go to this outpost city, they knew about how far did you go every day. Well, somehow they were able to measure about how far they went every day, and so how long did it take you, and then estimated the distance down to this Syene, the city. And that came out to be so many stadia, which today we call kilometers. And then x would be the whole circle. So whatever ratio it is in angles, it also has to be the same ratio in crust. Does that make sense to you? You guys are pretty high up in math. I bet you've figured that out. Can somebody put that in a calculator and tell me what you get? With his, since it was his video, I think he got 46,000. I thought it was less than that, but when I read some more stuff about Eratosthenes, the stadia, he was either off by 0.5 degrees or 0.5% or about 4%. He was either 4% off, depending on what you use for your measure for stadia. And I have to say that's pretty good to be less than 5% off when, number one, that was a pretty crude measurement, that stadia thing there. And even the angle, like that. So what would I have you do? How would I have you do this project? Let's say I wanted you to do this with a partner, okay? How would you set this up? And I'll tell you where it works really well. It works well right about this week. Sometime this week, and even next week. I think it would work really well for you to do that. You could set up some kind of a stick that you knew was vertical. You checked it. It was 90 degrees here, this way. It was 90 degrees this way. You could just put a stick in the ground and check for how straight up and down it was, right? You could do that. He talked about just having somebody hang a weight down, and maybe have a weight that you can actually buy. You don't have to buy it, but they have these weights in the hardware store called plumb bobs. You ever heard of that? You know what a plumb bob is? A plumb bob, P-L-U-M-B, get it? Lead, weight, plumb bob. Okay. So plumb bob, you can actually buy these, and they're actually pointed, and you can hold a stick, and Earth's gravity just simply makes it point down. You say, well, why would anybody use that? Well, people who build brick walls, how do they know they build them straight? How do they know they're building a brick wall? How does a bricklayer know that? And they put a string up there and hold a weight down. And they say, you're this far away from the string, so are you, so are you, so you see it? And that's how they make brick walls straight with a plumb bob. So whether or not you use a plumb bob or whether you have a stick like this, here's what we could do. You would have to have some way of measuring the sun's angle in Greensboro right up here. I see that? Now, we could do that. I think to do this project, one way you could do it, I wouldn't mind if we did it both ways, is to find this angle, okay? That's one way of doing it. What's another way we could? So if I find the angle at the top of the stick, then I can plug it in to this thing here. But how else could I find that angle? Yes?
Find the angle that's touching the ground.
I could find the angle touching the ground. There's another way. What's another way? Yes?
Find the length of the sides.
What is it?
The length of the sides.
Keep going.
Or you could use trigonometry.
Ah, okay. So we could use some trigonometry, couldn't we? So let's say that you knew this stick was 100 centimeters. Let's say you use a meter stick, or whatever you want to use. And then you could measure the shadow, could you? So you could measure the shadow. So which trig function would you use to find that angle or this angle? Which one would you use now? Okay, so let's try it. So tangent is opposite over adjacent, right? So as seen through the eyes of that angle, I'm opposite and you're adjacent, right? So here's a shadow here. I don't know what the number is. I don't know what that. I'm gonna call it X. So we could use trigonometry, and if you think you can get a pretty good measurement on that shadow, and you have a pretty good measurement on the stick, then I can see doing it both ways. I can see where you take the angle here and put that in the equation, and then you find that angle using trigonometry and find the angle that way. So let's say you're going to calculate it both ways, all right? You find it one way with the protractor, you find it one way with the trigonometry. Now, what else do you have to do? So let's say you find this angle, and by the way, it's not going to be close to 72. I'll give you a hint. In Greensboro is not going to be close to 72. You get that? Okay. Now, what about this? What else do we need? If you're going to do this in Greensboro, you need the angle. You need one more thing. What else do you need? Yes.
You need a point on the equator and know the distance from here to there.
Right. So what I'd like you to do is you have to look up someplace that, and I'll teach you a little bit of geography here a little bit. What are the lines on the globe? The lines that go this way. They go, and if you look at this globe here, here's the biggest one of those lines. It's called the equator. The equator is called 0 degrees. What do you call it? Starts at L. Latitude. And then you go up here and you get 30 and 60 degrees latitude. And notice the circles get smaller, don't they? The circles get smaller. And so you go north, you can go north latitudes, 30, 60, 90 north is the North Pole. And you can also go south, 30, 60, 90 degrees south latitude. See that? Now we don't want that, but we want these other lines. What are these other lines that we've decided to divide the Earth into? What are they called? They're not latitude lines, what are they? Somebody said. Longitude, aren't they? And or meridians. So longitude lines, what's interesting about them, they're all the same size, aren't they? So what we need somewhere, here's Greensboro right here, and we'd have to look up there the longitude line for Greensboro. And then we got to find somewhere on the equator that has the same longitude line. See that? It's a little bit of research, you can do that. So you find someplace that is due south of Greensboro on the equator. So I know you can do that. So anyway, then I should be able to calculate in two different ways. One, using some kind of a protractor, and two, using trigonometry. Yes?
What if you live in California and your point is in the middle of the ocean?
That would be harder. That would be harder for me. And it just so happens I've done this before, and I happen to know, let me find it. It's going to be in Ecuador. So it looks like it's going to be in Ecuador somewhere, okay? So we're lucky. We almost missed. We almost missed South America. So what I think would be interesting to do is to do this and see what we get. Now, I want to try to tell you why it works in the next couple weeks better than other times. It's not that I can't do it other times, but it works really well during this next couple weeks. All right, and if I could even tell you the answer. I just do this honestly, okay? I want you to do it honestly. But what I want to show you is something that a lot of people. Have I ever taught you about a globe ever? I don't think I have, right? It didn't come into play in chemistry. I don't see how it would. But see this globe? This is an older globe. And I'll tell you what I like of all the globes when I was younger, they all had these on there. And now today's globes, you don't even see these on there. I think they're afraid of making somebody, offending somebody because I put it right on top of your island. Okay, that's going to happen. If you want to put something on a globe, how about this, huh? Okay, see that look. Well, anyway, nowadays you don't even see this. Do you even know what this is called? Very resourceful, look at that. Good eyes. You're looking right at it, aren't you? Very good. This is called an analemma. Anna means annual, yearly, okay? Analemma, it looks kind of like a figure eight, doesn't it? See that? And what's interesting is everybody's birthday is on there. Everybody's birthday is on the analemma. And so, for example, I'm looking up here, and it says around June 21st, right there. See? That's interesting. And down here, December 21st. Oh, that's pretty interesting. And what about right here? What about when it crosses the equator, right here? September about 21st and somewhere around March 21st. What do you think about that? Okay, so what the analemma tells you is at what date is the sun directly overhead at noon? Oh, I didn't finish my story. I'm sorry. If you're going to do this project over here, when do you take that angle? Do you get up at 8 o'clock in the morning and your stick's ready and is that when you take it? No, because the shadow will be very long in the morning. As the sun comes up, what happens to the shadow? It starts moving and getting shorter. And then it'll start doing what? Longer and going that way. So what we want is, we really want the time when the shadow is the shortest shadow. Now they call that solar noon. Solar noon, not necessarily on your watch. We have daylight savings time, all kinds of stuff, don't we? The solar noon would be the time when the sun gives the smallest shadow on a stick, like that. All right, so here's the analemma. Let's go back to analemma. Ready? When is the sun's rays the most direct, directly overhead on January the 21st? It's up here. Now, what do you mean up here? Well, up here, I'm on a dotted line. I'm right on a dotted line here on the globe. Does anybody know what that dotted line is called? Did you guys ever have this in elementary? Did they ever talk about the equator? Did they ever talk about the Tropic of Cancer? Have you ever heard this? I'm looking at your faces. It's Monday morning, right? All right, so when you look at a globe, so what's a globe? Okay, when you look at a map or a globe, you're going to see the equator. See that? That's called 0 degrees latitude. All right, got that? Now, this analemma says the sun will be directly overhead on June 21st if you're anywhere at 23.5 degrees north latitude. 23.5 degrees north latitude, there's a dotted line called the Tropic of Cancer. Get that? Now, if you go down here, the sun's most direct rays are down here at 23.5 degrees south latitude in December 21st. Now, I need your attention here because this is pretty neat. What about these two things? If you're in North Carolina, what kind of weather are you having? What's it all about here, June 21st? And what about December 21st? So if I were looking in the summertime in Greensboro, if it was June 21st, then the sun would be pretty high in the sky. It would never be directly over my head. How do I know that? Because if you don't live within 23.5 degrees north and 23.5 degrees south, if you don't live in that band, the sun will never be directly over your head, ever, ever. And guess what they call that band between here and here? Starts with a T. It's a word they use all the time when they talk about storms. Okay? If they originate in this band, they're called tropical storms. That's the tropics. So you don't live in the tropics. You don't live in the tropics because you have to live between here and here to live in the tropics. Because you don't have any day in a year, no, never, is the sun directly overhead in Greensboro. Because you live up here. You live up here. So if you wanted to pick your birthday, you said, you know what, I always wanted to go somewhere where the sun would be directly overhead on my birthday. Find your birthday, find a latitude, and find some country you want to go to. See that? And then go there and be ready at noon. And then you'll see it. And you'll stand there in your shadow. You won't have a shadow except right underneath your feet. You put a stick in the ground, there won't be any shadow on the stick. You say, oh, I always wanted to do that. So that's what the analemma is talking about here. Now, the dates I'm looking at, the first, by the way, does everybody know what they're called? The first day of summer, first day of winter, what's that called?
Equinox.
The other one. Solstice, okay? So you have a summer solstice and a winter solstice, and they call it, for us, they call it June 21st, they call that the longest day of the year. We know that's not true. It's not the longest day. It's the longest amount of daylight hours. Of the 24, you'll see the sun the longest on that day. You see that? That's what makes it the longest day. It's the same amount of day. Get it? And what about what we call this one? December 21st. That's the shortest day of the year. It's the least amount of sunlight you'll ever see all year. And let's go to the other one now. What about these other two dates? The March and the September. What's that called? Go ahead. Okay, and the one in the fall is called the fall equinox or autumnal equinox, and the one in the spring is called the vernal equinox or spring equinox. Equal night, equinox. Everybody on the planet on this day, all right, will have exactly 12 hours of sunlight and exactly 12 hours at night. See that? So, if we do it on the equinox, we can do this experiment really easily. And I'll even tell you the answer, okay? I'll even tell you the answer so that you can do a percent error. We're gonna do percent error this week. You can do a percent error calculation this week on your project. So, if you were to look up, what's interesting, if you looked up Greensboro's latitude, right? 10, 20, 30, they might happen to know anywhere close. What's Greensboro's latitude? Anybody know?
45 degrees.
30.
You're getting there. It's less than 45 is more than 30.
35.
That's really close.
36.
It is about 36. So anyway, Greensboro is around 36 degrees north latitude. And again, I don't want you, if you do this project right, I don't want you to say it's 36. I'd rather you not know it at all. But I'd rather see what you get and then see what your percent error is, right? But if we do that, what's interesting is on the equinox, if the sun's most direct rays are at the equator, then we'll find your latitude. You can actually find your latitude on that day. And again, you can do it anytime in the next couple weeks. So I'll probably give you like until the end of next week or something like that. I'll even let you do it with a partner. I'll let you do that. Or if you don't want to, you can do it by yourself. Yes?
Is this in class or outside?
This would be outside class. I could do it, but you wouldn't be ready to do a stick tomorrow, would you? See, is it gonna be sunny like 2 days from now, or? I can do it on Friday, except we don't have class on Friday, but would you really? You might not want to do that on Friday, would you? See, I think we had to do it on a weekend, or you have to do it sometime when you, if you and your partner wanted to stick that stick in the ground tomorrow, the next day, or next day, or next day, or next day, or the next 10 days, at school, you could do that. That's all you need. You just need it in there long enough to get a reading, don't you? And it has to be in there long enough that you know when the shortest shadow is too, right? So anyway, I want to show you just a little bit about this. And so the reason that Greensboro will never have the sun directly overhead because we're outside of the tropics, aren't we? So I don't know if this helps you or not, but the next time you see those little dates on the calendar, think of it, it's not really just a date. It's a real astronomical event. I have some good news and bad news for you. December 21st, June the 21st was the longest day of the year, but guess what happens right after that? The sunlight hours slowly get shorter and shorter and shorter, and they go all the way to 12. They'll go down to 12 hours, and tomorrow's the first day of fall. Got some bad news for you. Guess what's going to happen again? What's going to keep happening? The amount of daylight hours are getting smaller and smaller and smaller until we get to December the 21st. December 21st will be the smallest amount of daylight hours we have. And then the good news, after December 21st, it'll be slow. You'll slowly get more hours of sunlight, more hours of sunlight. See that? So we're actually getting less and less sunlight every day. Now, there's other things. I'm not here to teach you astronomy. That'd be a neat class to have. But there's other things to think about is that when the sun is most directly overhead in June 21st, we get more direct sun rays for a longer period of time. That's why we tend to experience summer. We have summer because we get the longest amount of hours and the sun's more direct in the northern hemisphere. That's our summer. And I gave this for extra credit many years ago. I might still do it. If you could find someone or even write a letter or an email to some kind of a travel bureau in South America, Southern Hemisphere, and ask them for a calendar that has pictures on it. And what would we see in June 21st? On June, the calendar, you see people going to the beach, stuff like that. What are you going to see in like South America or Australia? They're going to be bundled up because the first day of summer for us is the first day of winter for the Southern Hemisphere. Oh,
I don't think
You
so.
think about that?
Really has winter though.
now it's true that Australia, because it's surrounded by water, it's not going to have as many of the extreme conditions that we do. What about the first day of fall tomorrow? What's happening in South America or even Australia? What's that called for them? First day of spring. It is. Everybody see how that works? Okay, so if you've never been taught that, I think that's worth it. So here's what I'd like to challenge you, all right? If you would like to do this by yourself, you can. But if you want to have a partner, you can do that also. Well, let's talk about this. Let's say by the end of next week. How about that? That give you enough time? By the end of next week, what I'd like you to do is to try to figure out what day you're going to be able to either stick a stick in the ground, or you could even, I don't know if you want to use a videotape. I wonder how you could do it using technology, but you want to put a stick in the ground and make sure you have looked at the shadows and figure out when solar noon is. Everybody get that? Solar noon. And what you really need is, you need the height of the stick, or if it's a plumb bob, you need that right there, and you need that length right there. And also, I want you to try to get the angle up here with a protractor, like that. So, anyway, with a protractor, figure out, and also you gotta look up one more thing. You gotta look up someplace in Ecuador that has the same longitude line as Greensboro, and then find that distance right there. Now what you do is you turn in your calculations and then do a percent error. Now to do percent error, you have to know what the target is, right? So you can look that up. You can look up Greensboro's latitude and see how close you got. So if your calculation said 45 degrees and you found out Greensboro is 36 point something, then you could do your percent error like that. All right, so I want to give you till next Thursday. You have till next Thursday for you to do it by yourself or a partner, and you need to do it somewhere solar noon. If you want to bring your stuff to school and set it up out there and just say at lunchtime, you could go check it. You could check it, say shorter shadow, shorter shadow. That's all you need. So you could do it at school if you want, or you could do it over the weekend.
Are you gonna sign partner?
No, I hadn't planned on assigning partners, but because some people are going to do it by themselves, so I didn't know about that. Let's see. What if I gave you 2 weekends? Would that give you enough?
Yeah.
So what if I said 2 weeks from today? What about that? Now, if you do it too far away from the equinox, that's going to make you have more error. Everybody get that? So I'd rather if you did it within 2 weeks of the equinox, I think you're going to get pretty good numbers. So I'll go over this again tomorrow. You pick a partner or do it by yourself and say, what I really need to do is figure out that. Am I going to stick a stick in the ground, or am I use a plumb bob? And how am I going to measure? If I have a string, like here, if I have a shadow here, I got to put a little card up here or something. How do I measure the angle? How can I measure the angle? Yes?
What format are we turning our stuff in?
I would say you're trying to find the circumference of the Earth without leaving Greensboro. That might be your title. And then you'd say, step one, here's what we did, and make a little sketch of what your drawing was. Here's my calculations using the protractor angle. Here's my calculation using trigonometry. And then do your percent error. So it probably fit in one page. Unless you want to get fancy and draw some drawings and stuff like that. Yes?
How much is this gonna be worth?
I thought it would be at least 30 points. 30 points for you and your partner to do this. It's really not as much work as you think. The main thing is figuring out how to do the stick. That's going to be more work than anything else, like that. All right. Well, let's think about that, and you could even research right now, or today, or sometime. You could research and figure out the other number you need, and then the main thing is to figure out how to put that stick in the ground. All right. Tomorrow,